next meeting, what I intend to do is go through all of the different aspects of motor testing, and particularly talking about the areas that bring the best results. And like I said, there are so many tests I can mention: partial discharge, capacitance, inductance, impedance, tan delta, surge test, ramp voltage, insulation resistance, polarization index, dielectric absorption. There are so many tests, but what truly are the ones that are effective? And, you know, do we waste our time sometimes testing for very obscure faults that could be done easily by utilizing faster, quicker tests in a more user-friendly way? And this is something that over the years I've found when I've visited different sites, I've asked them if they've had a motor failure or motor issues, which is usually why I was there being a contractor. They would say, yeah, well, we usually do these tests and we usually do those, and we're surprised that we can't, we haven't been able to stop this failure or similar failures in the past. And it's simply because, you know, the insulation, the root cause of the failure emanated from another area but wasn't covered in the test that they were doing. So, like I said, that I hope the webinar was interesting to you, and look forward to seeing you during the next webinar. Michael?
Okay, sir. Thank you so much for the presentation, and let's move on now to the question and answer. But before doing that, let me remind you that for those who are leaving, please don't forget to fill up the survey form that will pop up on your screen when you close the webinar panel. So now let's go on to the questions, Paul.
Sure.
Do we have time?
Okay. Yes, sorry. Yeah, of course we do.
Yep. So the first question is, what is the permissible motor vibration limit? What standards are used? What sensors transducer are used?
Okay, well, vibration analysis is is an area that can be looked at in many different parameters. There are people use velocity, acceleration, and different formats to measure the vibration. But overall, there are international standards that rate a particular application. So if you've got a big motor, let's just say the international standard says that this size motor or mixer or pump or whatever it is falls in class 2 type of machinery. And then the standard of acceptability for the vibration for that particular unit is the standard. So let's just say the International Standards Organization have depicted that 3 millimeters per second, which is a velocity reading, is acceptable for a class 2 machine, and that's maximum. So then when we come along with our vibration tester, what we're doing is we look at the overall vibration, and that means all of the vibration added together into one amount. And if that is over 3 millimeters per second, then what we can do is we can split those frequencies apart. So let's just say we had 5 millimeters per second as an overall number, and we had 1 millimeter per second at imbalance, 1 millimeter per second at looseness frequencies, 3 at misalignment, 4 at electrical fault, and 5 at bearing. So basically look along, and that's where the analysis comes in. But by the way, we can do all this on torque as well. So if we're looking at vibration, we can still test the bearings, but look by looking at the torque. So this is technology that is very, very relevant. But to answer the question about the standards, obviously different countries generally follow different types of standards, but certainly the International Standards Organization is one globally that most people follow.
Thanks, Paul. For another question from him also, from Ifan Prihama and from Indonesia. After how many rewinding should the motor be replaced with a new motor? What is the reason?
So the windings can fail through contamination for many reasons. The picture that is on the screen now, you can see contamination there. And what happens is during startup, you get approximately 8 times the current of the motor's full load capability surge through those windings. And that voltage that is going around the turns is looking at a way to get from A to B as fast as possible. So if it can jump over going around those turns and through contamination or moisture, etc., then it will do that, and it will create an arc and shorting and flashing. What we need to do is, by servicing electric motors, is to try and stop that from happening. Keep it clean, keep the motor windings varnished solidly so they're not moving during the operation, heating up and cooling down. You know, the windings can often move with that, and over a period of time they rub together and it damages the insulation between the turns and coils. So if it gets to a point where we've had a failure and we replace the winding with a new winding, it's been rewound basically, as long as the rewinder hasn't done any damage to the core of the motor or any other of the aspect, the rotor, and even during the failure, sometimes when a motor arcs over and blows, it can damage the core. But often the failure is in the overhang of the winding. And if the windings are removed in a professional, temperature-controlled way, then by replacing those windings by a rewinder should not be detrimental to the motor. However, there are lots of people that rewinders that may offer a cheaper price, that the reason how they would burn an electric motor out to basically melt the varnish so that and heat up the copper so it comes pliable enough that they can pull the windings out of the slots that go through the motor. By doing that, they can damage the core. So as long as they don't do that, by replacing the winding with good insulation, you can even improve the winding and the longevity of an electric motor by going for a rewind. And in that case, as long as you're replacing the bearings and you're measuring all the mechanical aspects as well, there is no reason why you can't rewind a motor over and over again. But in reality, I think a lot of the time electric motors kind of have a lifespan. So the core is made up of a series of laminations, and inside those laminations is a thin layer of insulation to stop circulating currents building up in the frame of the motor and the core. Now, the more physical movement and the more heating up and cooling down that they do, especially if the temperature is excessive, then that insulation can deteriorate, and therefore the motor will start to operate at a hotter temperature, and again could lead to premature failure of the windings next time. So there's no right or wrong. It's more of how the work is done to whether it's going to be suitable for for many repairs. So I'm sorry I haven't got an exact answer for that, but that's the truth.
Yeah, no, very well said, Paul. I like the answer. Now we have here a question from Muhammad Habib regarding the high voltage test for motor, for example, step voltage, surge test, DCRAM, and others. Is there a possibility that if we perform this high voltage testing, will degrade the lifetime of the motor? Is there any concern to perform?
No, and I touched on the answer to that earlier. When an electric motor starts, you can imagine the contactors in the panel. They come in, they're sprung, so they come in as fast as they can. But what happens in slow motion is, as those contactors come in, to make a connection, just before they actually make that connection, there's an arc. And that arc sends a spike of voltage through the winding that it sees every time it starts and stops. So when we do a higher voltage test, we're only emulating what the motor sees every time it starts, but we're in control of the current of the test. Whereas on startup, not only do you get this spike of voltage for that instant while the arc is in place, but the motor is also trying to start at 8 times its full load current. So let's just say it's a 400 volt motor. During that contactor, we might get a spike of voltage at 3000 volts. Plus, if it's a 100 amp full load motor, you know, during that same startup procedure, the motor's probably pulling 800 amps. So volts times amps is power. So during startup, an electric motor will see it'll be the worst condition of its life. Even if it's a VFD drive and we're changing the speed as it goes along, it's like changing the gears of a bicycle or a car. You kind of back off, and then when the gears kick in, you get another spike of voltage and energy goes through the winding. So VFDs, change of speed and frequency, starting and stopping, is very detrimental to motors. And what we do by using those high voltage testers that are controlled and also recommended by IEEE, IEC, ESA, you name it, all of the main bodies of people that give you recommendations of how you should test electric motors, they all recommend that we do these tests because they understand that there isn't a negative side. I think the question is born from some of our competitive testers that don't use this high voltage to identify that early insulation that can be spotted during the startup and stop. Because what happens is during that startup and stop of the motor, if there is weak insulation, you're going to get arcing inside. So by using the higher voltage during the test, even though the current is much lower, and there's no power in the circuit, we can still detect any potential weaknesses in the coils and the turns by using that high voltage, but we're not using the power of the motor and that could create damage. So I hope that explains it a little bit. It is quite complicated, but yeah, like I said, the IEEEs of this world have done done a lot of research into this type of testing, and it's still recommended, and it's the only way, by the way, and you mentioned the surge test, it is the only test available that can still predict, you know, so if you're using a surge tester, you can go up to a motor, you can test it, and if it passes, you can actually say, I've done as much as I can to make sure that my turn-to-turn and coil-to-coil insulation is strong enough that it's not going to be arcing and shorting during startup and stopping. No other test can do that. So and by the way, that is, I'll get into it more next week, but that is the root cause of up to 80% of electric motor electrical failures. It's the weakest insulation in the motor is not the ground, it's the insulation between the turns and the coils. So if we're not monitoring that, then we're going to miss 80% of our electrical failures, which is why do we bother almost with predictive maintenance if we're not going to start detecting those?
All right, very well said, Paul. Thank you so much for the answer. Yeah, maybe the last one because we're running out of time. And I guess these 3 questions that is here is all related. So how to check AC cryogenic motor?
Well, I'm not too sure what you mean by cryogenic. All AC electric motors have traditional windings, and the insulation on the coils and turns is generally can be a mixture. It's usually enamel on the wire that is very thin layer of varnish that's on the wire. In the core of the motor, you've got various Nomex, polyester style insulation that is all temperature rated. So if we have particular motors that are designed to work in hot environments or specific environments, maybe there's a chemical like some refrigerants and things like that which can eat into the windings, and then we have to apply very special specific insulation to combat that. But you can do it. It's not a problem. So for argument's sake, if it's a motor that runs in a very, very hot environment, we might want to use class H insulation rather than class F, which is the more common. Class F is got a polyester plasticky insert to it, which can melt and break down at I think it's 165 degrees, whereas the 180 degrees of the higher range insulation is usually the pure paper Nomex style insulation that insulates the slots or even mica in armatures. So those instruments that have those motors that have that kind of heat resistant, you can still apply the same tests. We're still looking for the same breakdown mechanisms in those motors. It's just that the insulation is designed to be more specific for the environment that it's in. But it shouldn't affect the way we conduct our tests in any way.
Right, so thank you so much, Paul, for the answer. And I guess we're running out of time. So for the other questions, we'll answer through email. And for any of you who have more questions, please send us an email. I think you saw the email address of Paul in the previous slide. So again, that concludes our webinar for today, and thank you so much for attending, everyone. Please have a good day and stay safe. Thank you so much, Paul, and thank you so much, Barry.
Thank you, everybody. Bye.
Thank you, Paul. Thank you, Michael. Thank you, everyone.